Okay, let's make a start then. So what we can do this week is to continue looking at this decision-making part of the UCAT test. So we started that last week, and it's going to take the whole of today to go through the rest of this. So it's taking a long time to go through decision-making, and just to emphasize, that's not because it's the most important section or in the end necessarily the most difficult section. It's just that the questions take more getting used to because it's not as obvious what's required as it is, for example, in verbal reasoning. So it's taking us quite a lot of time just to hopefully get you used to what the questions are all about. But once you get past this stage, actually getting good at them isn't necessarily any more demanding than it is in any of the other sections. Okay, so we looked at 3 sections last week. The fourth one is what they call the strongest argument section. So what they do in this is they give you a proposition, and then they give you 4 arguments either in favor of it or against it, and you have to decide which of those 4 arguments is the strongest. So, for example, they might sort of say the proposition is that the United States should take possession of Greenland by force, and it doesn't matter. I mean, hopefully you think that's a bad idea, but that's irrelevant, okay, because it's not about what you think, it's about what the arguments they provide in favor of it suggest. So a strong argument, what strength means in the case of this is that it provides evidence. Okay, so it's not about how persuasive the language is or anything like that. It's just about how strongly the evidence they provide backs up the argument or says, no, the argument's not going to be valid. And again, emphasizing it's nothing to do with what you think in each case. So what does it mean by evidence? Well, it's got to be factual. So it's got to say things like this is true and therefore that supports the argument, or this is true and therefore it means the argument doesn't make sense. It can't be just what someone thinks, so not an opinion. That's really important. It's got to be relevant. Sometimes they'll try and trick you because they'll give you something that's hard factual information, but when you think about it, you realize that it doesn't actually bear upon whether the proposition is valid or not. So the relevance you've got to check. And generally, the strongest argument, it's got to be clear why it's relevant. And sometimes they give you a more complicated proposition that has multiple parts to it. And then what you're looking for is evidence that bears on all parts of the proposition, not just some of them. Okay, so here's an example. A very simple proposition in this case. Should the British monarchy continue to exist? And you can see you've got 2 arguments saying yes, 2 arguments saying no. So which one do you think is the strongest? See what you think. Okay, so anybody want to make a case for any of them? Yep. Anybody disagree? No, so A is the right answer. I mean, in that case, it leaps out to you straight away as being more detailed than any of the others, and that might make you think, oh, that's probably going to be it, because obviously the more detail it's got, in principle, the more chance it has of being strong evidence. But you can't rely on that because obviously they can trick you by putting down lots of irrelevant information, for example. But in this case, it makes sense because it says that it talks about the money it brings in, and it talks about why that would be useful because you could spend it on infrastructure. So there's detailed evidence there saying it does a good thing, and it also considers the counter argument, which is oh, but it costs money as well. But it says, yeah, but it brings in more than it costs. So that's a good example of a detailed, compelling argument. But this section is different from all of the others. Remember in the other ones we said, once you spot the one that's right, you just ignore the rest. Because you can't really do that here, because there could be an even better argument lower down. So you've got to quickly look at the other ones before you say, oh yeah, it's definitely A. So B has one word in it which immediately should make you think it's not going to be that one. Spot what's the one word? Yeah, yes, some. Okay, because it's an inspiration to some citizens, and that's going to make you think, yeah, but what about the other ones? It's a weaker argument if it's got those sort of vague words in it, like some, and so those are really useful because you can sort of immediately rule it out based on that. Also, of course, it says it's an inspiration to some citizens, but it doesn't say what it's inspiring. I mean, it might be inspiring them to commit armed insurrection or something, so it's not necessarily a good thing. So again, it's not a convincing argument. C is sort of similar to A in the sense that it's focusing on the money, but you can see it's just got much less detail. So it doesn't consider the counter case, it only considers the cost and doesn't consider the fact that it's bringing in money as well, nor does it really say what the money is going to be used for, just could be used elsewhere. So it's not as good an argument. And D, what tells you that D is not going to be a good one? And there's a sort of a word there that gives it away as not being good. I think deserve is the word, because that tells you it's an opinion, right? Deserving isn't really something you can quantify. It's just that I don't, it's basically saying, I don't like the royal family, they don't deserve whatever. And that's an opinion, it's not factual information. So you can see it's not terribly difficult to get the right one most of the time. And so this section tends to be just about getting through it quickly. Usually it's fairly straightforward to pick the right one, but you've got to read quickly and spot the immediate reasons to throw out arguments, so you don't spend very long evaluating ones that are going to turn out not to be convincing. Okay, that's good enough. Well, this is just a sort of summary of the things to look for that mean that arguments are likely to be weak. So you've got to check it's relevant to the question. You've got to look in more complicated examples for when only part of the question is addressed, and we'll see an example of that in a minute. So ideally, a strong argument should deal with all of the ideas that it introduces in the proposition. And then look for vagueness words, some, possible, those kind of things. Look for words that tell you it's an opinion rather than a fact. And then ones that sort of have factual evidence, but you have to think too hard about whether it's relevant or not, are going to be less convincing than ones that make it absolutely clear why the evidence is relevant. So those are the sort of things to be looking for. Okay, so just look at one more of them, see what you think about that one. What's the best one in that case? Yeah, C, the third one is the best one. And again, you can see that that's because it's much more specific in what it's saying than any of the other ones. So this is a more complicated proposition. It's not just a one-line thing, you know, like the royal family one was. So convincing arguments got to cover spending on foreign aid, it's got to cover the fact that it's relevant to malaria, and it's got to cover infant mortality. And C is the only one that does all of those things explicitly. So it talks about malaria and talks specifically, not just mentioning malaria, but talks about how foreign aid spending could address malaria by providing bed nets. It talks about child death rates and makes it clear how those could be reduced. So it looks pretty convincing. All of the others are sort of relevant, but they're just much less specific. The first one, again, has one of those giveaway words, some, so you can rule that one out straight away. Okay, some countries, this may be a problem, but what about the rest of them? And also harming children is obviously a vague sort of thing. Harming them in what way? Is that relevant to malaria? Second one, again, it's only talking about some countries. Well, many is a stronger word than some, but it's still a slightly vague word. And you can see that it just doesn't address specifically the problem. So B, it's hard to sort of say that's clearly nonsense, but it's not got that detail that makes C convincing. And the last one is obviously extremely vague. No specific mention of malaria or child death rates. So C is the winner there, based on that. But you can see you had to look at all of them to make that judgment clear. Okay, so I won't spend any more time on strongest argument sections because you can see that it's straightforward enough to understand what you've got to do. And as you practice more of them, you'll learn to spot most of the bogus arguments very quickly. So the next section we're going to look at focuses on probability. So if you do A-level maths, this may be something you've revisited more recently. But for most of you, this is just harking back slightly to GCSE maths. But it's really not a very mathematical section. So it's not going to give you challenging calculations to do and things like that. It's really just about making sure you know what the definition of probability is. So if you've got something that you've measured multiple times, it's the number of times the thing you're interested in happened divided by the total number of events. And that, if you just work it out like that, comes out as a fraction between 0 and 1. Or you can multiply it by 100 and give a percentage. And they use both interchangeably. So you need to make sure you're comfortable with probability of 0.3 is the same as 30%, because they just use both in the questions. And most of the questions, really that definition is all you need. And you just have to think about how that probability would be influenced by the various factors that they ask you to consider. And what makes the questions challenging is generally not the maths, but the fact that they just present the information in an incredibly unhelpful way. So they don't give you nice organized tables most of the time to present the data. It's all in words. And as you'll see in the examples, often the way it's presented is potentially misleading unless you read it carefully. So here's an example. I'm going to suggest very strongly that you get some scribbling equipment out for this one, because again, it's one of those things that if you're not careful, you end up thinking about the same thing 3 or 4 times because you forget you thought about it before unless you scribble stuff down. Okay, anybody got an answer? Yep. People agree and we disagree? Yeah, so C is the right answer. So this is a very typical kind of question. Because when you first look at it, you think this is going to be really complicated because it says you've got to think about two things. You've got to consider what effect you're going to have on the probability of the coach's own team scoring a goal, and you've got to think about what's the probability of the opposing team scoring a goal or not scoring a goal. And as soon as you've got to think about two things like that, in principle, that makes it statistically complicated, and you think, oh, I'm going to have to combine probabilities in some kind of complicated way. And generally speaking, you're not going to be expected to do that in these questions. So there has to be a reason why one of those factors turns out not to be something you have to worry about. So why is that true in this case? What simplifies things in this case? Yep. That's right. So if you focus first of all on, okay, if I look at the effects of these two substitutions and I just focus first of all on the chance of the coach's own team scoring, it tells you that there is an 80% chance of the coach's team scoring a goal if player A is replaced. So you're going to compare that with what if players B is replaced, and unhelpfully, it gives you this information, but only indirectly, because it tells you there's a 20% chance of the coach's team not scoring. So the important thing is that you remember that the probabilities have to add up to 100%. So if there's a 20% chance of them not scoring, there's an 80% chance of them scoring, and that's the same. Okay, so you can therefore say, right, I don't have to worry about the chance of the coach's own team scoring because it's the same for both. So then you just focus on what's the chance of the opponent's team not scoring. So again, it's unhelpful, but the information is all there because it says there's a 70% chance of the opponent's team scoring. So again, you do the subtraction from 100 and say, right, that means there's a 30% chance of them not scoring if he substitutes player A. But if he substitutes player B, there's a 50% chance of them not scoring. So there's a higher chance of them not scoring, 20% higher chance of them not scoring if he substitutes player B, and therefore player B is the better bet. So that's why the answer is C. So you can see if they've given you that information in a table so that it was always probability of scoring or probability of not scoring rather than doing it in this messy way, it would have been an easy question. But it just takes time because you've got to wade through all this waffle and you've got to convert chance of not scoring into chance of scoring and stuff like that. So none of it's difficult, but it's just you've got to do it quickly because remember, these are all 1 minute questions. But very commonly, that issue there, that it starts out looking like it's going to be complicated because there's more than one issue to think about, almost always you discover that one of the issues is actually the same in both cases, so you can then just focus on the other one. That's a really important lesson from that example. Okay, so that was the answer. Let's have a look at another one. Anybody got an answer for that one? Yeah, B is the right answer, so well done if you got that one. So let's go through again. So again, you can see in principle this could be complicated because it's saying which is the better investment option, and you think, well, does that mean which one has the best chance of getting a really high yield, or which one has the least chance of getting a really low yield? You know, and it's not clear which one you've got to focus on. So you think, oh, that's complicated because I've got to think about both things. But you're going to expect, having had the experience of the last one, that one of those is going to turn out to be the same for both. And that's the low yield, because it tells you there's a 0.7 chance of stock earning 12% or less. And for gold, there's a 0.3 chance of it earning more than 12. Therefore, 1 minus 0.3 is 0.7 chance again of it earning 12% or less. So the low yield is the same for both, so you don't have to worry about it. And that means that for both of them, there's a 0.3 chance of it being somewhere between 12% and 100%. And the question is, how is that distributed between the middle range, 12 to 50, and then the 50 or above? So you can see that for stock, it tells you there's a 0.1% chance of getting that top range, 50% or more. So what you've got to do is work out what's that probability for gold. So the last line, you've got a 0.1 chance of it being between 12 and 50. You add that to the 0.7 chance of it being less than 12. It adds up to 0.8, so you've got 0.2 left. You've got a 0.2 chance of getting 50% or more. So it's a higher chance than the 0.1 you had for the stock. So that's why the gold is better. So you can see the real close similarity to that first question. At first you had to work out which bit of the apparently complicated problem actually wasn't an issue. And then you had just relatively simple maths. Really the only probability rule you needed for both of those questions was to realize that the probabilities add up to 1 to 100%. And that was the only maths involved in both of those. Okay, so sometimes you might have to combine probabilities for more than one event happening. So this one isn't a UCAT question, but it's just to make it clear what I mean by combining probabilities. So if you've got two independent events, so independent means that if you flip a coin and throw a die, the chance of you getting a 6 with the die is independent of whether you got heads or tails with the coin, because obviously they're completely separate things. And so if you've got two independent things like that, the question is, what's the chance of this being true and that being true? So in other words, of getting heads and a die, and the die equaling 6. Or the other way of combining them is, what's the probability of getting heads or of getting a die, or potentially both? So I'll just give you a minute or two, just see if you know how to do those things. One of them is much easier than the other, and the more complicated one I think you'd be unlikely to need. So don't worry too much about it if you don't know. But I'll just give you a minute or two, see if you can work those out. Okay, so the first one then, you can see that the probability of getting heads is a half, and the probability of getting a sixth is a 6 with the die as 1/6. So what's the probability of both those things being true? Yep. Yeah, so you just multiply them together. Okay, so that I think you need to know. So you may have forgotten that, or maybe never even have learnt it. But if you are asked what's the probability of this happening and that happening, and provided they're independent things, you just multiply the two probabilities together. So 1/2 times 1/6 gives you 1/12 for that one. The or one is more complicated. Anybody get a number for that one? Yeah. Okay, 2 and 3. Anybody disagree? Agree? Actually, not quite right. It's 7/12. So let me just show you how you get that one. So the top one you can see was just, as I say, 1/12. For the or one, you have to consider the 3 possible ways you could get heads or a 6. So first you say, well, you could get heads but not a 6. So you multiply a half is the probability of heads and 5/6 is the probability of not a 6. So you get that. Then you consider, okay, I could get a 6 but not heads. So that's 1/6 times a half. And then you've got the probability that you could get both, which is a half times a sixth again. So you add those 3 together and you get 7/12. I think that it's very unlikely you would need that one. So if you're looking at that thinking, I don't want to think about that, that's too complicated, I'm not going to be able to do that, I don't think you're going to need to. I had a look through all of the questions in their own database of practice questions, which was a joy, and you didn't ever need that. So the or one I just put up there sort of for completeness, but I think it's unlikely. And I would go as far as saying that if you find yourself trying to work out something like that, you're probably on the wrong track. But the and one, the idea of just multiplying probabilities, that you might just need. So we can just kind of summarize then the things that you need to remember. So say learn that multiplication rule. Most of the questions, really the only thing you need to remember is that the sum of all the probabilities of all the possible outcomes must add up to 1 or to 100%. First couple of questions, that was really the only thing you needed. Third one, as I say, I think it's very unlikely you would need to, what's the probability of this or that happening? And the last thing is just to sort of say that if you want to understand how probabilities combine, tree diagrams are much the best way of visualizing it and convincing yourself that those rules make sense. But you obviously don't have time to do tree diagrams in a UCAT exam. So don't start going down that route unless you just want to, for your own peace of mind, kind of convince yourself that those things make sense. So probabilities adding up to 1, and then that simple combining things when it's this happens and that happens is, I think, all you need. Okay, so let's look at one more example. Okay, so what's the answer? Do you agree or disagree? Yeah, A is the right answer. So there are basically two ways you can approach that question to get that answer. One is simply to realize that what it's really saying is, right, in order for him to get home on time, the bus has to be on time and the train has to be on time. So if you want to actually work out the probability that he'll get home on time, it's just that combining probabilities rule. Okay, so you say, right, well, based on the numbers you've got there, 4 times out of 5, or 40 times out of 50, but therefore 4 times out of 5 the bus is on time, and 4 times out of 5 the train is on time. So the chance of both of them being on time is 4/5 times 4/5, which is 16 over 25, which is more than half. So there's a greater chance than not that he will get home on time. So that rule gives you the answer A straight away, as yeah, that's right. You could, though, work it out without actually doing that calculation if you weren't comfortable doing the calculation. So if we just look at the other possibilities, so starting at the bottom, that's a really interesting one. Was anybody tempted by D? D is quite an interesting one because it might well be that part of your brain is saying, well, that's right, isn't it? That it doesn't really matter what happened yesterday and the day before. You know, today is today, and all that really matters is what's going to happen today. So why should you convince yourself that that's not a good way of thinking? Not particularly from this, but just in general. Why should that? It doesn't really matter what happened yesterday because today is a new day, sort of thing. What's the problem with that line of argument in terms of your career plans? How does evidence-based medicine work? Yeah, well, I mean, because the only evidence you have is what happened yesterday, isn't it? So as you say, you've got to have evidence, and the evidence is what's happened in the past. So when you make a decision, okay, I'm going to treat this infection with antibiotics, you do that based on evidence of what's happened in the past when this infection's been treated with antibiotics. You know, what's the probability that the patient got better, and what's the probability that the patient will have had bad side effects or whatever. And it's not that you'll necessarily have those numbers in your head, but the clinical guidelines that you'll have in your head will be based on those numbers. So if you're going to embrace the way medicine and dentistry are practiced, you have to accept that the evidence you're basing it on is what's happened to when other people were treated in this way in the past, and therefore what's the statistical likelihood that it will work in this case. And it can't tell you what will happen, of course, that's the thing. All it can give you is probabilities. So every time you treat a patient, you can't think this will definitely work, because there are always going to be, you know, differences in individual patients and so on, differences in what happens on the day, which will mean you can't say for sure, but probabilities are what you're going to have to use to guide you. And of course, that's why they put this section in, because they want to sort of get you used to thinking in that kind of way. So D is an interesting one. And you have to say, well, no, you can't think like that, that what's happened in the past will give you evidence as to what's likely to happen in the present. So it's not going to be that one. What about C then? So 20 occasions over the 50 days, either the train's been late or the bus has been late. So it's unlikely he'll get home on time. You can imagine yourself kind of thinking that while you're sort of taking a sort of slightly pessimistic view of what your chances of getting home on time. But what's the problem with that argument? Yeah, I mean, it's sort of dodgy at two levels, but if based on those statistics, the maximum chance of you not getting home on time is given by the fact that on 20 out of the 50 days, so 40% of the time, one or other of them was late. So, 40% of the chances, in your head, you're thinking, well, that's quite a high chance. That's not something I'm very excited about, but it is less than 50%. So in the worst interpretation of those data, you would say, well, it's more likely than not that you will get home on time. But of course, that's not the way you should treat the data, because what does that ignore? If you just add up the probabilities like that, what are you ignoring? Yeah, so you're kind of assuming that either, on some days the train is late, on some days the bus is late, but of course on some days both of them will be late. And that's what you miss out if you just add up the probabilities like that. So it's not mathematically sound, but that doesn't matter, because that 20 out of 50 is the maximum it could be if it was true that they always happened one or the other on separate days. Even then, it's less than half, so that's clearly not right. And what about B? So B is kind of saying, well, it may not matter if the bus is late, because if the train's late, you might still catch the train. But what's the flaw with that one? Yep. Yeah, if the train's late, you're going to be late anyway, so it doesn't matter that you caught it, because it's going to be late anyway, so you won't get home on time. And you might think, well, what if the train caught up some time on the journey? But that's starting to get a bit sort of far-fetched at that point. So you can see that if you didn't want to do the maths, you could actually rule out each of the other three and end up with A, but that was a lot more involved. It was actually quicker just to combine the probabilities and work out that A was correct. Okay, so enough about probability and statistics. As you can see, it's not really a mathematical challenge. It's mainly just getting used to the kinds of questions and being organized with the information. So normally they just bombard you with too much information. So you've got to start scribbling things down, making sure that you keep track of everything, and then the questions are not too bad. So the last section we're going to look at are again a hark back to stuff that you probably studied in maths at some point in the past. Well, if you're doing statistics, you may have returned to these more recently. So everybody familiar with Venn diagrams? Nobody's looking at that thinking, what the hell is that? No. Okay, so see then, if that's what they mean. So the circle represents the set of people who are Norwegian, the rectangle, the set of people who wear glasses, and the triangle are the set that reads poetry. So if you just scribble that down and then see if you can do that, just to make sure that you're comfortable with how these things work. Okay, so that's what we should have got then. So there are 5 people for whom each of these things is true. So they're Norwegian and they wear glasses and they read poetry. So that's the triple intersection in the middle there, which is within the triangle and within the circle and within the rectangle. And then there are 12 people who are Norwegian and who read poetry but who don't wear glasses. So they're outside the rectangle, but they're inside the other 2. Okay, so as long as you can do that, then that's really the only sort of maths content for these Venn diagram questions. So you think, oh, that's all going to be very easy, but the way they make it slightly less easy is by giving you Venn diagrams like that. Okay, so see if you can work that one out. Okay, so what's the answer? Yep. D, anybody? Yeah, you agree, good, right, well done. Yeah, D is the right answer. So if this was on paper, it would be kind of easier because you could sort of, draw around the relevant bits and things like that. But of course, it isn't going to be on paper, it's going to be on a screen. So this is actually what you're going to be faced with. But it's actually not as difficult as it looks. So you think, right, well, let's start with the gold first of all. So it's got to be within the double-headed arrow, and it's got to have diamond in it. So it's got to be in the bit of the double-headed arrow that's also within the rectangle. And that then narrows it down to actually just 4 numbers that are included in that intersection. And it's got to have silver as well. So it's also got to be within the heart. So that narrows it down just to 2 then. So you've got the 75 and the 23. But it's got to exclude platinum. So it's got to be outside the pentagon, and that just leaves you with the 75. So that's got to be the answer. You think, well, what about the pearl? But that's okay because the pearl isn't within the arrow anyway. So 75 is your answer. So it's not that hard, but again, it's just keeping track of the information, making sure that you don't get overwhelmed by the number of numbers that you're trying to keep in your head. So scribble them down if that helps. Okay, so D was the right answer. Now this is a bit different. This time it gives you some information at the top, and then it gives you 4 Venn diagrams, one of which is consistent with the information at the top, but the other 3 are not. To see if you can work out which is the one that fits with the information. Okay, so which is the right one? See any disagreement? Agreement? Yeah, C is the right one for that one. So there are loads of ways to approach that. And in these things, you haven't got time to work out what's the most elegant way. You just got to plunge in and come up with a strategy and do it. So I did it just by saying, well, you've basically got 3 big sets there. So you need to have corresponding to the 3 ovals. So you've got to have one with 20 in it for geography, one with 20 in it for history, and one with 12 in it for art. And if you just do that, you realize that A doesn't work because, for example, the top oval has 25 in it, so that's no good. B doesn't work because the top oval has 17 in it. C works though because each of the ovals has 20. On the right hand side has 20, and then you've got 12 on the left there. And D doesn't work because you've got 17 on the bottom left. So without even looking at the intersections, that was a quick way to do it. But you could, for example, have started with the fact that you've got to have that triple intersection of 5, where they all want, which of the people who want to take all 3. So that would have ruled out D, and you could work backwards from there. So lots of approaches. And I think once you've started with one, you just have to keep going. So it's not about finding what's the most efficient way, it's just getting it done as quickly as you can. Okay. So this one is a bit different because this time they don't give you a Venn diagram to look at, they just give you the information and you have to work something out. But you can see that it's the same kind of problem because you've got sets of people, male or female, adult or children, and there are going to be intersections and so on. So there are 2 ways to approach this. You can just view it as a numerical problem. So if you like juggling numbers, potentially doing a little bit of algebra, you can approach it that way. Or you could scribble down a Venn diagram, which might be something like that. But that they didn't give you, so you would have to come up with that and then start putting the numbers into it. And it's just up to you as to what you think works best. I mean, I just did it by juggling the numbers, but if you find the Venn diagrams helpful, then just plunge straight in and do one. See if you can work that one out. Okay, what do we think? Yep. A is right, is 3, yeah, okay. So as I say, you can just do that numerically. So you start with the fact that there are 27 people, and of those 3 more are male than female. So you can work out how many males and females there are. You can do that if you want to be rigorous and mathsy by doing a pair of simultaneous equations, but it's easier just to juggle the numbers in your head and think what 2 numbers add up to 27 that differ by 3, and you get 15 and 12. As I say, simultaneous equations would give you that if you want to do it properly. So you got 15 males altogether, because there are 3 more males than females, and then it tells you that 12 of those are adults. So 15 minus 12 gives you 3 children. So you can see in that case, the numbers worked out quite quickly, and it would have been a waste of time constructing a Venn diagram. But of course, that's always a bit of a gamble because sometimes it may get more messy than that, and the diagram could be useful. So there's there's always going to be an element of gambling. So yeah, that would have been the sort of Venn diagram approach, but it's quicker just to do it with the numbers in that case.